Okay, so as we ended the last video, I was asking you to take a look at this function. I wanted the intervals on which the function was increasing and decreasing, and then the location and value of any and all relative maxes and mins. All of which requires that I know the derivative. So I'm going to look at f prime of x, and this looks like a chain rule problem. The derivative of the natural log is the reciprocal, so I'll take the reciprocal of x squared plus 9 times the derivative of the inside part. So that's going to be 1 over x squared plus 9 times 2x. And I can just write that as 2x over x squared plus 9. Now, that is a fraction, so I do want to be conscious of checking for if it's ever undefined. It would be undefined if the denominator was 0. But at the end of the last video, we pointed out this is always positive. So this is going to always be defined. So I want to see where it's equal to 0. So when is 2x over x squared plus 9 equal to 0? Well, here I'm going to use the fact that a fraction is 0 provided that the top is 0 and the bottom is not 0. Of course, if the bottom was 0, it would be undefined. I would have already dealt with that, okay? But a fraction will be 0 if just the top is 0, provided I know that the bottom isn't. Now that becomes a whole lot easier. That just means that x is equal to 0. So I've got one critical number. It's 0, so I'm going to draw my number line for f prime. I'm going to mark off that critical number of 0, and then I'm just going to pick some test numbers. So I could pick -1. If I plug that in, I'm going to get a negative divided by a positive, so it's going to be negative. If I pick a number to the right of 0, I'll pick 1. I'm going to get a positive over a positive. That's positive. So we're going down and then up. So I can say that f is decreasing on the interval from -infinity to 0. I get to throw in that finite endpoint because my original function was continuous. And I know it's continuous because that's a polynomial, and that's the natural log function is continuous, and I just combined them via composition. So what I built is also continuous. We're increasing on the interval from 0 to infinity. And looking at the shape of the graph, I can see I have a min here. Looks like we don't have any relative maxes at all, but I do have a relative min. So f has a min when x is equal to 0. If I want to be more specific, I can say it's a relative min. Okay. And the min is f of 0, which would be the natural log of 9. Okay. Excellent. Okay. So the first derivative is incredibly useful in telling me what the function is doing in terms of is it going up or down, and then that information in turn is very useful in figuring out where I have maxes and mins. Do be careful though, and don't assume that a critical number has to be either a max or a min. I want to just take a look at a real simple example. If f of x is equal to x cubed, f prime of x would equal 3x squared. Now, that's always defined, certainly. Okay. That's going to equal 0 if x is 0. So I could draw my number line. Okay. This is for f prime, mark off my critical number. But when I plug in a test number, regardless of what I plug in, because I'm squaring x, it's going to be positive. So f goes up, and then it goes up. We don't change direction. If f doesn't change direction, I don't have a max or a min. Okay. Now, the derivative being 0 does still tell me something about the graph. I know what x cubed looks like. It's kind of an S-shaped graph. At least that's what people say. I don't really see the S there. Okay. Now here I drew it fairly carefully. I made sure that there was a horizontal tangent at 0. I know there has to be because the derivative is 0 at 0. If I'm just drawing things real quick, I sometimes draw it more like that. Well, that's not accurate. It actually does have a horizontal tangent there. But you'll notice it doesn't change direction, so that horizontal tangent isn't the location of a max or a min. Okay, we'll keep this video kind of short. The next one we're going to come back and take a look at what the second derivative tells us about the graph of a function.